Hi, I'm Yin Kai, and today I would like to share with you a work I have with Earl Campbell on the trade-offs on number and phase shift resilience in bosonic quantum codes. Now, this project is a topic in quantum error correction, and in quantum error correction, we want to protect, say, a logical qubit against noise. And this can be achieved by introducing redundancy in the quantum information, for example, by encoding the logical qubit into multiple logical qubits. However, in this paper, we are interested in the topic of bosonic quantum error correction codes. So instead of using qubits, we use qubits, where each qubit has a potentially infinite number of energy levels, which corresponds to an infinite number of dimensions in the qubit. Now, we are interested furthermore in a particular family of these bosonic codes known as rotation-invariant codes, which were recently studied by Grismo, Combs, and Barrighello, have this very nice structure when on a single mode. And I write a structure on a single mode for simplicity. Namely, they are gapped in a Fock basis. When you write down the superposition of any state in these rotation invariant codes, they must have this structure. Their Fock states need to be gapped G apart. And these gaps intuitively help with the number shift errors that are, for example, modeled by, and one important example are like amplitude damping errors, which model energy relaxation in physical systems. However, another type of error that you may want to consider are phase errors, which also occur naturally in physical systems. You can model them using this Gaussian dephasing channel, where the probability P is given by a standard normal distribution, well, with a standard deviation of sigma, and these phase errors are modeled by these phase operators over here, written in the number basis. And if you evaluate the action of this Gaussian dephasing on the Fock basis, you can find there's a very nice closed analytical form, which makes it very easy to work with analytically. And moreover, as I mentioned, these codes are very natural. They arise in any physical system that can be modeled by such a master equation over here. Now, we're interested in the paradigm of approximate quantum error correction. We say that a code is approximate error correcting if and only if, for every state that you pick within the code state, you apply noise and then you do the best you can to recover the noise. You always have the trace distance between this corrected state and the original perfect state to have a trace distance of at most epsilon. Conversely, you can say, using this definition, you can say that, well, the code is not an epsilon error correction code, approximate error correction code, if there exists a state within the code space such that the error is too large. And the main result of our paper is that once this epsilon is too large, where this threshold is given by this number over here, then the code cannot be an approximate quantum error correction code. So over here, this threshold has these parameters G and sigma. As you can recall, G relates to the resilience against the number shifts, and sigma is the strength of the Gaussian dephasing errors. It's the standard deviation of the Gaussian dephasing errors. So a case where there's no noise will correspond to sigma equals to 0, and G is really a parameter of the rotation invariant code. Our result also generalizes to multiple modes, but we write this equation on this slide for simplicity, although for the proof we do it for multiple modes. And also we note that whenever G times sigma is above this threshold, then you can't have this epsilon going arbitrarily close to 0, which means that when G times sigma is above this threshold, one must tolerate a finite amount of error in using these rotation invariant bosonic codes. Now we can plot the our numerical results over here. Our results for a single bosonic for codes on a single bosonic mode. On the y-axis, you have this minimum approximate quantum error correction error epsilon, and on the x-axis, the horizontal axis over here, you have this the strength parameter of the dephasing errors. As you can see, when sigma is too large, you can't have codes above this line. So as long as you're above these lines, you can't have codes with the corresponding parameter of G. As you can see, when G becomes larger, which means that you have more resilience against number shifts, you would have less resilience against these dephasing errors. So there's this trade-off that which we have quantified precisely, which we have quantified in our theorem, and which we illustrate in this plot over here. And to prove our result, we rely on this key fact. Now, consider positive numbers A and B, and suppose A plus B is at most C. Then we can make the trivial conclusion that either A is the larger one or B is the larger one, in which case A will be at most C over 2 or B is at most C over 2. And similarly, you could flip the sign to go the other way. A plus B is at least C, and then there must be one that is the smaller one, and hence A is at least C over 2 or B is at least C over 2. Using this key fact is what gives us our lemma, our theorem. So first of all, we begin from a lemma, which is a reverse triangle inequality. So suppose that you have two states, row 1 and row 2 on the code space, and they are orthogonal. So I've drawn them to be separate circles over here. Now, the condition that the trace norm of n, the channel acting on them, or the difference between them, is at most delta, implies that the code is not epsilon AQEC, where epsilon is given by 1 minus delta over 2. So note over here, row 1 and row 2 are basically any states within the code space. And to prove this, we use a reverse triangle inequality. So basically, we start from the term on the right-hand side, and we note that it is at least this term over here by the reverse triangle inequality. And because row 1 and row 2 are orthogonal states, we know that this trace norm over here must be equals to 2. And so we can rearrange this inequality and get this inequality over here, which is very nice. And then we apply the triangle inequality on the left-hand side, and we obtain this inequality. Then we use the fact that if you have two positive numbers that are summed to be at least another positive number, then one of them must be the smaller one. So we must have either row 1 minus this thing to be at least this thing, or row 2 minus this thing to be at least this number over here. And since row 1 and row 2 must be states within the code space, this implies that the code cannot be epsilon quantum error correcting when the epsilon is 1 minus delta over 2. And now we are ready to go on to the next lemma, which is to prove an upper bound on basically these quantities over here. We want to prove upper bounds on this quantity over here. So let's write down what a logical 0 and a logical 1 would look like for this. And you can write it in the Fock basis. And basically, we consider stabilizer states, the plus, the minus, the plus I, and the minus I. We can write them down like this, and you will see that they have these forms over here. And what we are going to do is we are going to evaluate the Gaussian dephasing channel on the plus state minus the minus state, and the plus I state minus the minus I state, and evaluate this quantity over here and obtain an upper bound on it. And we're going to show, we can easily find that this norms will be at most this thing over here, and where we have these sums over these A's and the B's. These terms over here are at most equals to 1 by Cauchy-Schwarz inequality. And hence, it is easy to see that using this fact, since we have the Cauchy-Schwarz inequality, the sum of these two norms is at most this, and using the fact of the sum of this, if you have two numbers a plus b at most c, and they are positive numbers, then we have this condition over here. We can see that, well, we can see that at this term over here is at most half of this term over here, or this term over here is at most half of this term over here, and from which we obtain an upper bound on basically either one of these differences over here, and from which we can obtain the upper bound on the channel acting on the difference between the states, from which we can apply the previous lemma, which was the reverse triangle inequality, to prove our result. And so we can also illustrate the performance of known bosonic quantum error correction codes with respect to our no-go bounds. So binomial codes are a known example of rotation invariant codes. Let's see how they perform when G is 64, say. And so over here, we have these binomial codes. Binomial codes have this error over here. Yeah, and this is the no-go bounds over here. So we have so we can see that we have a gap over here. We don't know whether it's our no-go bounds that are tied, that are not tied, or whether it's the binomial codes that are not tied, but it's most likely both that are not tied. And we can also answer the question of achievability of quantum codes if you use multiple modes. Can using arbitrarily many modes help to have the error to be arbitrarily low? And if one wants to answer this question, this is really a question of the quantum capacity of Gaussian dephasing channel, with the added constraint that the code must be supported on this must have this rotation invariant structure where the Fock states are gapped. And we can achieve a lower bound for the quantum capacity by observing that effective qubit states that are spanned by this 0 and G over here is a subset of all possible rotation invariant states. And by using the effective dephasing by using this effective dephasing channels, quantum capacity, which we know, we can obtain the result that actually for any G, no matter what your G, as long as you let the number of modes becomes arbitrarily large, you can have these, you can make the approximation error arbitrarily low. And so, some open problems would be, okay, we've analyzed the trade-off between G and this dephasing errors, the strength of the dephasing errors. What about replacing this number shifts with photon loss errors? For example, the amplitude damping errors, where the probability of energy loss is given by some parameter gamma. And also, what is the performance of these celebrated Gottesman-Kitaev-Preskel states with respect to phase noise, and what's the scaling with respect to photon number? So these are questions that remain unanswered, and we think that future work in this direction would be very interesting. Thank you for tuning into my talk today. Have a nice day. Bye.